K cross E equal to say omega mu H, and the K cross H is equal to minus omega epsilon E cross E. Okay, and we know that K dot D is equal to 0, and K dot B is equal to 0. We have already derived the normal surface equation from these two equations. Okay. So if I substitute the second equation to the first one, I get K cross Yeah, I do the K cross operation to the first equation. So I get this equal to omega mu K cross H. K cross H can be we can substitute the second equation into this K cross part, okay, minus omega squared mu epsilon dot E. So according to vector analysis, we know that this quantity, this combination of vectors can be written as E dot K dot E times K minus K dot K, which is equal to K squared times E. And this is equal to minus omega squared mu epsilon times E. Here, epsilon is the permittivity tensor. Okay. So now, if we use the so-called principal axis to be our coordinate system, we choose our coordinate system to have axis along the principal axis. So in this principal axis system, the epsilon has the simple form, has this diagonal form. Epsilon x 0, 0, 0, epsilon y 0, 0, 0, epsilon z. Okay. So if I take the x component of this equation, I get K dot E times Kx minus K squared times Ex, which is equal to, when I multiply this diagonal matrix to the column vector E, Ex, Ey, Ez. The x component of this epsilon dot E is just epsilon x times Ex. So here we have minus omega squared mu epsilon x times Ex. Okay, which means that K squared minus omega squared mu epsilon x times Ex is equal to K dot E times kx. Okay. So the ex is just equal to k dot e times kx over k square minus omega square mu epsilon x. Okay. Similarly, we can find Ey is k dot e times ky over k square minus omega square mu epsilon y. Okay, and Ez is equal to k dot e times kx. 等一下，我看一下 k yeah k square minus omega square mu epsilon z. Okay, so we have already learned that in general, k dot e is not equal to 0 because we have learned that this k, this d, and this is the direction of h. Okay, k is perpendicular to d, d is perpendicular to h, h is perpendicular to k. And in general, the E vector is in the KD plane. Okay, E belongs to the KD plane. Okay, so E can be written as, say, E dot S times S plus E dot, say, D. Here, S is the unit vector along the K direction. S is the unit vector along the K direction. And the D, the small d hat, is the unit vector along the D direction. Okay, so the vector E is along, in general, it has the component along the S direction, and it also has component along the D direction. So in general, K dot E, in general, K dot E is equal to this part times K times this part. Okay. So in general, this is not equal to 0. This is not equal to 0. Okay. So if this is not equal to 0, we can have a small conclusion that the E vector, if we want to know the direction of E vector, the E vector is simply written as this column matrix. The E vector is just being given by this expression, kx over k square minus omega square mu epsilon x, and ky over k square minus omega square mu epsilon y, and kc over k squared minus omega squared mu epsilon z. Okay, in the principal axis system. Okay, and this quantity is in fact proportional to this Sx over n squared minus nx squared, Sy over n squared minus ny squared, and the Sz over n squared minus nz squared. Okay, so you see that in the textbook, we have two different expressions for the direction of E vector. The first one is the equation 4.2-9. This one, okay, this one, without this vector. And the second one is the equation 4.2-11, which is this one. Okay, this one. You have learned that here nx squared means epsilon x over epsilon 0, and ny squared is epsilon y over epsilon 0, and nz squared means epsilon z over epsilon 0. Okay, three reference reflecting this system. Okay, so according to this equation, or according to or according to this equation,我把这个擦掉。Now, if I multiply kx with this equation and multiply ky with this equation, kc, multiply kc with this equation and sum over them, then I get kxex plus kyey plus kzec is nothing but k dot e. Okay, so k dot e is equal to k dot e times the three factors kx squared over k squared minus omega squared mu epsilon x plus ky squared over k squared minus omega squared mu epsilon y plus kz squared over k squared minus omega squared mu epsilon z. Okay, so I get this equation. So if k dot e is not equal to 0, if k dot e is not equal to 0, then I get this n squared sx squared over n squared minus nx squared plus n squared sy squared over n squared minus ny squared plus n squared sz squared over n squared minus nz squared equal to 1. Okay, so if I divide the whole equation with n squared, I just get the same equation as in the textbook, the 4.2-10, which is the Fresnel's equation of wave normals, or the normal surface equation. OK， 从这里到这里，就是我把那个 c 分之 omega 平方 n 平方分子分母都除掉。OK， 没有把 c 分之 omega 的平方除掉啊。I just factor out the omega over c square in the numerator and denominator. Okay, so I get this expression, and this is the Fresnel's equation of the wave normal. 好，所以这样我们就有了一个更简单的方法去得到这个相同的方程式啊。那So if I divide the equation by n squared, I get this equation. Fresnel's equation of wave normal. So this equation gives us the solution of the desired refractive index. Okay, we can solve this equation for finding the corresponding refractive indices. Once we have a propagation direction, Sx, Sy, Sc, propagation direction, the small s is given by Sx, Sy, Sc. Then I substitute this Sx, Sy, Sc. In general, we can solve this equation to get two possible n1 and n2. Okay. Once we know the n1, n2, we get E1, E2, and D1, D2, and the corresponding H1 and H2. Okay, you can also write down B1 and B2. In fact, we can prove that D1 is orthogonal to D2. E1 is orthogonal to D2, and E2 is also orthogonal to D1. Okay. And S is orthogonal to D1 and D2. Okay, this is very obvious because we already know that the D vector is perpendicular to the S vector, the K vector. So this result is trivial. Okay. However, if we want to prove this, we can use the expression of E vector. Okay, then multiply the expression of E vector with epsilon. Epsilon is epsilon x 0, 0, 0, epsilon y, epsilon z, which is equal to epsilon 0 times nx squared 0, 0, 0, ny squared 0, 0, 0, nz squared. Okay. You can multiply the epsilon to the expression of E vector to get the expression of the D vector. Okay. Then to calculate the E1, you use refractive index N1. And to calculate E2 and D2, you use refractive index N2. Then you calculate this property and use this equation. Use this equation, the Bonnell's equation with normal, to prove this conclusion. Okay, I can show one to you. For example, the first one, and you know how to do this one. Okay. 如果要证明这个东西的话，其实是很简单的哈。第一个，其实我们可以先把这个方程式改一个样子啊。This equation not very convenient to use. I can change its form to another form. So it is more convenient to use. I can multiply the equation by n squared. In fact, I get the previous equation I derived, okay, and use the fact that S is a unit vector, so S dot S is equal to the square of the absolute value of this unit vector, which is equal to 1. And this means that Sx squared plus Sy squared plus Sz squared equal to 1. So I substitute this 1 with Sx squared plus Sy squared plus Sc squared. So according to this equation, note that n squared over n squared minus nx squared minus 1 times Sx, okay, plus n squared over n squared minus ny squared minus 1 Sy squared plus n squared over n squared minus nz squared minus 1 Sz squared is equal to 0. And this is nothing but nx squared Sx squared. You may notice that this equation is in fact equivalent to this equation, because we already derived the expression of the three components of Ex, Ey, Ez is proportional to Sx Sx over say Sx over n squared minus nx squared, Sy over n squared minus ny squared, and Sz over n squared minus nz squared are the three components proportional to the three components of E vector. So if I want to know the three components of the E vector, I just multiply epsilon x, epsilon y, and epsilon z to the three components of the E vector, which is proportional to the nx squared, ny squared, nz squared times the three components of the E vector. And k is proportional, the three components of k is proportional to sx, sy, sz. So finally, I get this result. Okay. So this is equivalent to the so-called Bonnell's equation of wave normals. Okay. And in fact, if I multiply this equation with n squared minus nx squared, n squared minus ny squared, n squared minus nz squared, I multiply this factor to this equation, I get an equation of this form. Which is a quartic equation, fourth power equation. Then I solve this fourth power equation, I get 2 possible n squared. Okay, I treat it as quadratic equation of n squared. I get two solutions, n1 squared and n2 squared, and then I take the roots of them, I get n1 and n2. Okay, the two possible refractive indices. Okay, so this result is this one. Okay, so if I want to derive this result, I can use the similar method. Okay, in the denominator, you will encounter this. If this is correct, then it means that nx squared times sx squared over n1 squared minus nx squared times n2 squared minus ny squared plus the similar terms equal to 0. Okay, so how can we get a denominator like this? Okay, it's not very difficult because say if I consider this, I get I consider this term. This gives us n1 squared minus nx squared, n2 squared minus nx squared. Okay, and this sub minus this one give us n2 squared minus n1 squared times nx squared sx squared. Okay, so I can we can find that we have this. So we can consider two Bernay's equation of wave normal in this form, and multiply them. One used the n1 and the other used the n2. Then subtract the second one from the first one and multiplying them with this factor, then I can get this result. Okay. You can change the coefficient of these two terms, so you can prove this one. Okay. Because if you want to derive this one, you will encounter something like the fourth power of nx, okay, without n1 and n2。好，这边就留给你们自己去证明啊，就课本上4.2-16的结果啊。The equations in the textbook 4.2-16。好，那接下来我们要推一个东西呢，是我们将来会用到的。好，好，我们刚刚讲的这个呢，其实说明了一件事，就是说这个 anisotropic 介质呢，跟 isotropic 真的有一点不太一样。如果是 isotropic 介质的时候呢，我给一个传播方向，我的电场只要落在跟传播方向垂直就好，它的偏振要落在哪个方向是完全没有关系的，都是同样的折射率。可是，在 anisotropic 介质里面呢，当你给定方向的时候啊，它会有两个特征的折射率，那两个特征折射率会对应到两个特征的偏振。OK， 那如果你是任意偏振，其实会看成是这两个偏振的叠加，它不对应一个固定的折射率，而是这两个分量的叠加。So, in usual isotropic medium, when I consider the propagation direction, the k vector direction, we know that the E vector is perpendicular to the k vector. However, the E vector can along any possible direction. The only restriction is that the E vector is perpendicular to the k vector. So the E vector can rotate to different directions, but we still have the same refractive index. Okay. However, in anisotropic medium, when we are given a propagation direction, the S vector or K vector, we have two eigen polarization. Okay, the two eigen polarization. The first one is called E1 or D1. I use D to represent the polarization because D vector is more convenient to use because it is perpendicular to the K vector. Okay, we encounter two possible polarization. The first is D1, the other is D2. The D1 polarization gives us refractive index N1, and the D2 polarization gives us refractive index N2. Okay, if we consider an arbitrary D vector in the D1, D2 plan, we will not get arbitrary n refracting index, but we can only treat the d vector as the superposition of d1 vector and d2 vector. The d1 vector has its own refracting index n1, and d2 vector has its own refracting index d2. Okay, this property is very useful. We will know how to use this property to design some useful device in Chapter 5。好，在第5章的时候，我们就会看到这个东西怎么用，其实是非常有用的一个特性。OK， so let me derive some useful equations which will be used later. We already know that we have K cross E equal to omega mu H, and K cross H is equal to minus omega epsilon dot E. Here we can just write this epsilon dot E as D. We want to know the direction of D vector. So according to these two expressions, the first expression tells us that the H vector can be derived from the K and E vector, omega mu K cross E. Okay. However, we know that K is equal to N times omega over C times the unit vector S. Okay. So if we substitute this K expression into this equation, we get H. H is equal to this one, N omega over C S cross E. So this is equal to mu C N over mu C S cross E. Okay. H vector is equal to N over mu C times S cross E. And what's the D vector? When you get the solution N1 and N2, you substitute N1, N2 into this expression, N1, N2 and E1, E2. You substitute the N1, N2 and E1, E2 into this expression, you will find H1 and H2. Okay. Now I want to know what is the D vector. D is equal to minus K over omega cross H. Okay. Which is equal to minus 1 over omega N omega over C times S cross H, which is equal to N over C S cross H. Okay. So once you know the H1, you can find the D1. In fact, it is not. You do not need to get H1 first and then to find D1. You can just multiply the epsilon matrix to the E vector, so you can get the D1 and D2. Okay. However, if we substitute this expression of H here, we will get this minus N over C S cross N over mu C S cross E. So this is equal to minus n squared over mu C squared times S cross E. S cross E. Okay. And according to vector analysis, this is just the S dot E times S minus S dot S is equal to 1. Okay, so finally I find that D is equal to n squared over mu C squared times E minus E dot S times S. Okay. Why is this? I have told you that E in general has two components. The first component is along the S direction. The second component is along the D component. Okay. So E is written as E dot D times D plus E dot S times S. Okay. Here D hat means the D vector divided by its magnitude. Okay. So E minus the projection of component along the S direction, we get this. I may use notation ED to write this part. ED times D hat. Okay, so I get D equal to n squared over mu C squared times ED times D. Okay, this part can be defined as the transverse component okay. The transverse component of the E vector. This part is perpendicular to the S vector or the K vector. Okay. So now we have this relation. D is n squared over mu C squared times the transverse component of the E vector. Okay. So according to this relation, if I calculate D squared, here this means the magnitude square. Okay, D squared is equal to n squared over mu C D dot E minus E dot S. Now, because D is perpendicular to S, D is orthogonal to S. Okay, so this is equal to n squared square over mu c squared times d dot e. So I get this relation. Remember what d dot e means. We have learned in chapter 1 that the energy density U E is equal to 1/2 E dot D. Here I use the real part expression, not the complex part expression. OK， 这意思是这样子的，就是说我们现在这个一啊，我们现在这个一或 d 其实是10或 d0的意思啊。The e or d here you can treat them as the E0, D0, the coefficient of the E vector, D vector. Okay, because they are linear polarization wave, so you can ignore all possible phases. Okay, and treat these vectors as real vectors. However, if we take the time average, you know that the total EM energy density is 1/2 E dot D plus 1/2 H dot B. For sinusoidal wave, so for plane wave, the electric field energy can change into magnetic energy density and change back. 对，就它们会一直交互变化来变化去，所以在一个周期内，这两项的平均值其实是一样。So in one cycle, the time average of this part is in fact equal to the time average of this part. Okay. So finally, we know that the electromagnetic energy density is in fact proportional to the electric field energy density. Okay. 好，那现在这个东西呢，这个是什么意思呢？这个 d 豆的 e 或 e 豆的 d 就是2倍的 u1 嘛。So this is in fact equal to 2n squared over mu c squared times u e. Okay. However, I have already told you that in optics, usually mu is equal to very close to mu0, and the 1 over c squared is equal to epsilon 0 times mu0. Okay. So this means that we have 2n squared over mu0 times mu0 epsilon 0 times ue. So now you get this 2n squared epsilon 0 ue. Okay, you get this? So this equation in fact tells us that we find that d squared, we can write the n squared as d squared over 2 epsilon 0 u e。好，我这边先停在这里哈。我们先下课，下课10分钟，好。